Thank you very much. Thank you for the invitation. It's great to be here. So, molecular hydrogen is one of these few simple atomic molecular systems that can be calculated from the first principles with extremely high accuracy, including higher QED corrections. So this is especially true in its ground electronic state. So this is one reason why we like the ground electronic state of H2. And other reason is that the rho vibrational states in the ground electronic state are ultra long living, million seconds a week. So this really puts the fundamental limitation on accuracy really low. So we started our adventure with molecular hydrogen from a typical cavity enhanced measurement. So in our first measurement, we simply placed the gas sample into two mirrors. So actually that was a bit special cavity enhanced setup because our finesse was over 500,000. As far as I know, that was the highest finesse ever used for molecular spectroscopy. And with this room temperature, at that time room temperature measurement, we reached 100 kilohertz accuracy in the measurements of the rho vibrational energy, which corresponds to testing the QED correction at fifth significant digit. And now so that was the beginning, and now the idea was to move this cavity enhanced this cavity enhanced technology into deep cryogenic regime. So the idea was to build a large cryogenic vacuum chamber. So it is almost so the system is like a vacuum inside a vacuum. So we have the gray layer is a room temperature vacuum, and inside the yellow layer, this is like an inner cryogenic chamber. And these two vacuums are independent, so we can fill the interior with H2 sample. And now for ultra accurate metrology, what is really crucial is to have a perfectly uniform temperature, to have a very well defined shape of a resonance. So we cool down not only the gas sample, but the entire cavity. So the two mirrors are cooled down, and of course the sample, the spacer, and the mirror position actuator also operates at down to 4 Kelvin. So that was the idea we had like 5 years ago, and then we spent few years on developing the setup. So we really designed and manufactured by ourselves, and part was outsourced to some R&D companies. And this is the heart of our setup. So this is this almost meter long cryogenic vacuum chamber that we can cool down to 4 Kelvin. So to avoid thermal losses, we suspended this really heavy chamber on a thin titanium rods inside the 40 Kelvin shields, and all this structure is suspended on stainless steel springs to room temperature chamber. So the thermal isolation is nearly perfect, but also this structure consists this structure really attenuates external and internal from the cryocooler noises. So we have very heavy stages that are suspended on the very thin wires. It's really typically when you operate high finesse cavity in the lab and you knock the table, then you lose like all the signal. And here we can really bumping the table with our hands, and the locks are maintained. So this shows how much we reduce all the external and internal noises. Yeah, and I cannot resist myself from saying this story. So we had really spectacular failure on the way when we've been developing the setup. So designing the cryogenic systems to large extent is about having ultra pure copper. This means that the conductivity is very high at low temperatures, and ultra pure means mainly oxygen free. So when we manufactured all the cryogenic stuff, and so we ordered from different companies from Los Angeles this 6 nines purity copper, from Finland another components, from Colorado some high conductivity thermal links. And the last stage before launching everything, to release the remaining tension in the material, you have to anneal the material. So we sent all the components to a huge company who was supposed to anneal it, but the technology person who was responsible for that, he confused the valves and sent oxygen into the chamber. So we like destroyed all the structure, and it took us almost a year to restore it, but we didn't give up. We rebuilt everything, and the system actually turned out to work better than design. So the assumption was that the assumption was to cool down the cryogenic chamber to 10 Kelvin, and actually we are able to cool it down to 4 Kelvin. So the gradient between the optical cavity and the cryocooler, which is 2 meters apart, is much less than 1 Kelvin. So that was the developments on the cryogenic part. And on the laser side, so for several reasons, it is good to work on the fundamental band in molecular hydrogen, which is at 2.2 microns. So we decided to build this high finesse optical cavity at 2.2 micron. And for that, we developed a system that is based on optical parametric oscillator. And that was kind of question mark for us, whether we can lock the idler beam of the optical parametric oscillator to a high finesse cavity by modulating the seeding laser of the optical parametric oscillator. So in theory, the modulation should propagate to the idler beam, not to the signal beam. The signal is determined, the frequency of the signal beam is determined by OPO cavity. And it turned out that the system works really well. We have a very high efficiency of injecting the idler beam at 2.2 micron to the high finesse cavity. So here you can see that we sweep the laser frequency, and these very sharp structures are narrow cavity resonances. And the high finesse means that the width of the structure is much smaller than the free spectral range. So one thing is that we managed to lock the OPO to the cavity, and the other thing is that the optical parametric oscillator provides almost 3 watts of continuous laser power at this wavelength, which means that we will be able, we haven't done it yet, but we are very close to do it, that we will be able to saturate the transition, the very weak quadruple transition in H2. On the way, when we've been developing this system, we made a good bit of really exciting engineering, and this is one of example. To operate a cavity and to do spectroscopy, we need to have tunability of the cavity length by at least few wavelengths. So in our case, this will be at the level of 10 microns. And we developed such a piezoelectric mirror position actuator. But the special thing about this is like that small device. But the special thing is that it not only works at 4 Kelvin, but the challenge was to make a mechanical structure that when you align a cavity at room temperature and then cool down the cavity from room temperature down to 4 Kelvin, it does not got misaligned. And we suffered a lot during these developments, but finally we ended up with a solution which works perfectly. So we can cycle the system back and forth from room temperature to 4 Kelvin, and the cavity is perfectly stable and aligned. So this is how it looked like the last moments before launching the system, jumping around the table and and a few months ago we finally get it. So we demonstrated that the system is fully operational, the finesse is maintained, and so we started from room temperature with finesse as designed 30,000, and it was maintained. So this picture showed a photon lifetime inside the cavity. And this 26 microsecond means that the finesse is there, the transmission is the same as in the room temperature. And then right now we are in the process of collecting the scientific data. So this is, so we really are able to measure molecular spectra in a gas sample in a temperature from 5 to 20 Kelvin. This is not a molecular beam, this is just a gas phase spectroscopy. And comparing to room temperature, now our line is almost an order of magnitude narrower and order of magnitude higher. There are also all other species are perfectly frozen. So we are we removed a huge huge portion of the systematic effects that people typically suffer from during. Yeah, so at room temperature it is so this is at the level of 200 megahertz. At room temperature is over gigahertz. So we haven't concluded the measurements yet, but we will for sure improve the previous measurements by at least order, if not. But we need to like measure at different pressures, at different temperatures, analyze the systematic effects, right? So for sure we will improve by order of magnitudes, maybe even closer to 2 orders of magnitude, the previous measurements. So this is like the one goal is to measure the structure of H2 isolated molecule, right? But the large part of activity of my group, independently from these experiments, are ab initio line shape calculations. So we for different reasons, for different applications, we do extensive calculations of collisional effects, collisional perturbation of molecular lines. And H2 is especially attractive from this perspective because this can be calculated accurately. So we calculated the pressure broadening cross-section and pressure shift cross-section. So these are these black curves. And if you average them over thermal distribution, you will get pressure broadening and shift. So here I'm talking only about the collisional effects. This depends on the regime we work in. When we go, it's mainly Doppler broadened, So that's for metrological purposes, we want to go as low as possible. But this setup gives us an access to study also the collisional, the physics of molecular collisions. I can, depending on we haven't measured at 4 Kelvin, we measured at 5 Kelvin. And the pressure is very low at 5 Kelvin, so the effect is small. But the thing is that molecular hydrogen, due to its small mass, it turns out that already at few Kelvin, the collisional effects are dominated by a single partial wave. So different colors here means different partial waves. It is not S-wave scattering, but this is a D-wave scattering, but we are already in a regime when the anti-collisional effect, collisional broadening and shift are dominated by a single partial wave. So this is, that was a cryogenic cavity setup. And now if we look at the fundamental limitation and the progress that has been done in the field in recent decades, so we can see that the black points are measurements before invention of optical frequency comps, and the blue points are measurements done with optical frequency comps. And now there is the fundamental limitation related to the lifetime is that there are still 12 orders of magnitude of potential improvement that can be done, and the present developments with cryogenic cavity or with molecular beams may give maybe 1 or 2 further orders of magnitude in accuracy. And to really explore this huge potential, we need to work with cold trapped molecular sample. And this is our new project we are developing in my group. So we want to trap cold molecular hydrogen. So the idea is that we have a cryogenic chamber and we have a 5 Kelvin source from which we will effuse in a collision, in a regime which is almost collision free, we'll effuse a 5 Kelvin sample into a high vacuum cryogenic chamber. So we are developing like a fast valve that will open a pretty large 1 millimeter diameter hole in a very short time to effuse a 5 Kelvin sample, and then we will launch extremely strong dipole trap with a depth of 0.2, 0.4 Kelvin. So we will trap or recapture the coldest fracture of the initial 5 Kelvin cloud. So we are so simulating the process. So the idea is that we will turn on the dipole trap in a very quickly, in a time that is comparable to the time of flight of a molecule through a beam. And then our simulations show that we should trap between 10 to 3, 10 to 4 molecules, depending on how over-optimistic we are in the calculations. There is another approach proposed by a group from Berkeley, from Holger Muller group. They suggest to work with a static trap, but very quickly decrease the pressure. So to very quickly go through the collisional regime when you can load the trap with collisions, and then very quickly decrease the pressure. So within this process, they will lose 2 or 3 orders of magnitude of the initial density, but in the end, they also estimate that they should end up with 10 to 3, 10 to 4 molecules in a trap. And with this new setup, we will be able to test these 2 scenarios. This is how it looks in our lab right now. Sorry? Yeah, so the system is nearly the same, but we will check both strategies using exactly the same system. This is how it looks today in the lab. So the cryogenic structures are almost there. We are testing this fast cryogenic valve to effuse the beam. Now we are installing the REMPI laser, the trap laser will arrive in a few months. And in a parallel to this, we are trying to work out also on a theory side what can be potentially done. So we are checking what are the fundamental limitations for our, so the H2 cannot be, it doesn't have a strong transitions that we can use for cycling transition for cooling. So we are checking what are fundamental limitations, how it behaves in magnetic field, in laser field. So we proposed something which we call like new type of magic wavelength. So if we use the fact, so we were a bit we had a bit of luck. So it turned out that H2 molecule has of course anisotropy in polarizability, and depending on the rotational state of our spectroscopic transition, depending on the magnetic number, the two polarizabilities are mixed in a different way. And by it is a coincidence that we can remove like over 90% of AC Stark effect by choosing a proper magnetic number of the excited states. So this is one thing. And then we demonstrated that the residual AC Stark can be removed by closely tuning the trap laser to one of the weak quadruple vibrational lines. And this, so yeah, but for molecular hydrogen, far-detuned laser means 300 kilohertz because the lines are that narrow. Then we are checking whether we are proposing different types of possible sympathetic cooling for future steps. And for instance, recently we've been checking what are the rates of inelastic to elastic, elastic to inelastic cross sections for H2 lithium collisions. So possibly we can, once we trap, hopefully H2, then we can think about some type of implementing some type of sympathetic cooling. Okay, so yeah, I think I'm still 4 minutes, but yeah, thank you.
Okay, thanks, Piotr. So now we have plenty of time for questions. Are there questions in the audience?
Vibration, which you call as zero. And this is the only transition which you want to measure in this when you have the hydrogen in 4 Kelvin. Or you also plan to measure other transitions?
Yeah, so we plan to measure S0 is like a default one, 0-1 vibration, S0
0-2.
Yeah, from rotation from 0 to 2. But so we already measured with our initial tests that the ortho-para conversion takes between 3 and 5 days. So then we have like 3 days to measure ortho if we want. So we can measure also Q1 or S1 lines too. So you can measure both ortho and para.
Yeah, but so this is the 2 transitions which you measure and you will stop. Means what are your long-range plans?
Yeah, so with this setup,
yes,
we have a whole bunch of things we want to test. For instance, when we started measuring this, we haven't like planned this, but it turned out that by simply doing the spectroscopy at different temperature, because we are working in the saturated vapor, pressure vapor conditions. So we, for instance, scanned the H2 phase diagram from 4 to 15 Kelvin for now. So we can, for instance, we will provide a very accurate measurement of H2 phase diagram. Another thing is that we realized that, as you pointed out before, the line broadening is mainly determined by Doppler broadening. So if we measure the width of the line, the frequency measurements are done with respect to the cesium clock from our NMI Polish. So then from this width, we can calculate the temperature. So this is like a primary temperature standard at deep cryo regime. So we can we can calibrate the sensors. So we already see that that our optical temperature measurement are consistent with calibrated diodes. But a nice thing is that we measure frequency, and if we want to go from frequency to Kelvin with new SI units, there are only 2 constants, Planck constant and Boltzmann constant. We need to multiply or divide the frequency to get the Kelvin. So this is like another thing. Another thing we want to do is, we haven't done it yet, but if we detune the laser by a few gigahertz, we will automatically see the H2 complexes. We can put helium inside and we will see H2 helium complexes or H2 argon complexes. So then there is like a whole bunch of things we want to measure once, and also these collisional studies. Yeah, so in the collisional community, there is a huge discrepancy. So people who calculate the collisional effects in collisional broadening and shift, it's almost perfectly agrees at temperatures from 100 Kelvin to room temperatures and beyond. But below 50 Kelvin, there are huge discrepancies, either over 100%. And there are only old measurements from few decades ago, and now we are at the position when we can provide very accurate measurements and very accurate theory for the collisional effect. So this is like another like way to go with this setup.
So when you're measuring the frequency to very high accuracy in this optical cavity, would you expect to get actually a line shift due to the interaction with the cavity, like polaritonic effects? What kind of line shifts would you get from that?
You mean the effects due to the cavity itself?
Yes.
Oh no, we are far from this. So this is a very long cavity, almost a meter long. Yeah, no, but this is not not this regime at all.
Thanks for over here. Yeah, thanks for the talk, Piotr. So, questions about this trapping with a very deep dipole trap.
Yeah.
So, I imagine you would have some AC start shifts from this. And the second question is that I was wondering, this also induces a very strong magnetic field from this photons. And the question is, will that change the ortho to para conversion rate? Perhaps, because the coupling changes in a magnetic field. And this is a very strong...
Yeah, I like the second question. Yeah, I the first also, but the second. So yeah, if we do this the experiment quick enough, quicker than 3 days, then
so this
should
is
be like
with the optical cavity around it. It'll take 3 days or so, you estimate.
yeah. So now there's like a typical number when you speak with people who work with cold H2. That if we put in a chamber which is not like magnetic.
No, but you can change the coupling. If you apply an external magnetic field, you change the coupling. So I wonder if the optical field.
This is a great. This is a great. I understand your question.
I think it's an interesting, maybe an interesting experiment on its own.
So there will be three optical fields. There will be trap. There will be like the spectroscopy laser and then the RAMPI laser. But the thing is that this is an amazing question. I like it a lot. The thing is that my estimation for the density in a trap is that I hardly be able to see any collisions.
I see.
If I can squeeze them, then I haven't thought about this. Yeah, but we can. Yeah.
No, it's interesting.
Yeah. As for the Stark shift, then I told you about this cancellation of the effect, and the Doppler effect will be larger than the Stark shift.
I see. Okay, thanks.
Okay, I think they were extra questions, but to keep the schedule, we will thank Piotr again.
Thank you.
And we will welcome the next speaker. So our next speaker